In this video, we're going to do an example using Snell's law of refraction. So over here we have an incoming ray of light, and then it gets refracted at the surface, and then it's refracted again when it leaves that material. So let's do a quick review of Snell's law before getting into this problem. So if we have a beam of light or a ray of light coming in at an angle, so coming into some material, some kind of surface, and the index of refraction of the material that it's going in is different than the index of refraction of the material that it's leaving. So we'll call this N1 and N2. These are just properties of the material, whether it's air or water or glass or plastic, just some kind of transparent material that light passes through. So if we have this ray of light coming in at an angle, then it's going to be refracted at this surface, and it's going to leave at a different angle. So depending on the index of refraction of the material, it may be kind of bent inward toward the normal line, or it may be bent outward. So the normal line, which is the line that we measure our angles from, is just the perpendicular line to the surface. So it's kind of an imaginary line perpendicular to our surface. So we'll have the first angle measured from the incoming ray of light to this perpendicular line. That's our theta 1. And then we'll have the outgoing ray measured from the bottom part of that line, and that's theta 2. So these are the variables in Snell's law, and Snell's law states that n1 times the sine of the first angle, the incident angle, is going to be equal to n2 times the sine of the outgoing angle. So let's go ahead and look at this question. We have a beam of light that enters a 0.5 centimeter thick sheet of plastic with an index of refraction of n equals 1.5 from air, which has an index of refraction of 1.0, and it exits on the opposite side. What is the angle of refraction of the beam inside the plastic if the beam originally, looks like I forgot an I in originally, if the beam originally entered at an angle of 20 degrees from the normal? And then also, what is the angle of refraction as it exits the plastic back into the air? So we have our index of refraction here. This is our index of refraction of air. That's N1. So that's air. And that is equal to 1.0. And N2 is a plastic, and it has an index of refraction of 1.5. So that's the index of refraction of this material here. And then it goes back into air, which is out here, N1. And so our first angle is 20 degrees. So that's this angle here, our incident angle. Call that theta 1. And for this first part of the problem, our angle that we're measuring for is this tiny little angle here. And that is theta 2. So we're first solving for this angle. We want to know the angle that it is refracted while it's in plastic. So we're going to use this equation. We know n1, n2, and theta 1. So we just have to solve for theta 2. So we're going to divide both sides by n2 to get the sine of theta 2 is equal to n1 over n2 times sine of theta 1. And then we're going to take the inverse sine to get theta 2 by itself. We take the inverse sine of n1 over n2 times sine of theta 1. So yes, we do have a sine of theta inside of an inverse sine, but don't get too scared of that. All we have to do is plug in these numbers, and then we'll have a number in here that makes you more comfortable. So then we have the sine, inverse sine of n1, which is 1.0 divided by 1.5 times the sine of 20 degrees. So just plugging this part into a calculator, we get the inverse sine of 0.228. And this is going to be 13 degrees. So theta 2 equals 13 degrees in the plastic. So this is the first part of our question. And now we have the beam leaving the plastic and going back into air. So we can just kind of blow this part up so we can see it a little bit better. So now we have N2 up here and N1 down here. So this is inside of the plastic. So we know this angle here is 13 degrees. So we'll call this theta 2 equals 13 degrees. That's what we just found. Now we have our beam of light leaving the plastic and going back into air. So it's going to be refracted again. So now our light is displaced a little bit, so it moved within this plastic. And now we have a new normal line here. So what we're looking for is this angle here. We'll call this theta 3, since this is the third angle we're dealing with. Now, how do we find the angle up here, our new incident angle? So luckily, if we know some geometry, we know that this angle is also just going to be 13 degrees. So this angle is also theta 2, 13 degrees. Now we can use some trig to figure this out. We actually know the distance here as 0.5 centimeters, and we know this angle here, or we can just look at the fact that this is 13 degrees, so this must be 90 minus 13, and because we have a right triangle, this angle here is going to end up being 13 degrees. So, however, we can also just use the fact that if we have two right triangles, then these two angles are going to be the same, and then these two angles are going to be the same. Therefore, we have 13 degrees here. So now we can just go back and use Snell's law again to find our new angle. So this time we kind of have it as N2 as our kind of first material times the sine of theta 2, which is our 13 degrees, is going to equal N1, since we're going from N2 to N1, times the sine of what we're calling theta 3. And we want to solve for theta 3, and we're going to just do the same order that we went up here, and we're going to end up with theta 3 equals inverse sine. Now we have N2 over N1 times the sine of theta 2. So that is inverse sine of 1.5 divided by 1. Of course, you don't have to actually divide this by 1, since you're just going to get the same answer either way. And then we have times the sine of 13 degrees. And this is actually just going to give us 20 degrees. So we're back to the angle that we started with. So 20 degrees for theta 3 when we go into the air. So hopefully that was helpful and not too confusing. We're actually just using a very straightforward formula here. So this formula for Snell's law. And anytime we're changing the material that we're going into, so you can do it from air into water or from air into plastic and then back into air, or sometimes you'll have a completely different material that you're going into after that. But you're just using this equation kind of over and over again if you're going into different materials. And it should also just be mentioned that, here, let's make some room here. If you have a ray of light and it is entering perpendicular to the surface, so straight into the surface and not at an angle, then our original angle here is 0, right? So theta 1 equals 0. And the sine of 0 is actually 0. So when you have your Snell's law equation, we have N1 times sine of theta 1 equals N2 times sine theta 2, and this is of course N1 and this is N2. What's going to happen to our ray of light when it enters into the second medium? Is it going to be refracted? Well, let's see. So if we put in 0 here, we get 0 equals n2 times sine of theta 2. So if we divide both sides by n2, we just have 0 equals sine of theta 2, and then that means theta 2 equals inverse sine of 0, which guess what is also 0. So that means if we come in perpendicular to the surface, we're actually just going to go straight through and there's no refraction. So that's something to keep in mind if you have one of those kind of conceptual questions asking you what happens if you go into a different material. Are you using Snell's law? Yes, you can technically use Snell's law, but you don't need to because you know if it comes in perpendicular to the surface, it's just going to go straight through without being refracted. So hopefully that was helpful, and soon we'll have some more optics examples in here, possibly a different type of Snell's law example. So thanks for watching, and let me know what other kind of videos you guys would like to see.